Hi, welcome to the Exponential and Logarithmic Functions. This is part one, and we're going to look at a lot of interesting functions here, which are important in modelling certain practical situations in the real world. And we're going to look at the derivatives of it, of course, as well, because the exponential function is a function looking up here now, which is increasing at an increasing rate. And a log function is a function which is increasing at a decreasing rate. Do you remember any of that? Oh, well, not to worry. We'll revise all of that and have a look at some of these interesting things here. E to the x, what's that? And ln x. So some excitement coming up now. Let's come on down and have a look at a revision of exponential functions. Here we are. So exponential functions are of the form f of x equals a to the x. And there are two cases. Come over here, look over here. A is greater than 1, so you could have something like 1.2 to the x, 2 to the x, 5 to the x. And as you increase x, of course, you're increasing the power, and because the number's bigger than 1, it's going to get bigger. So all of them are increasing functions. Increasing functions. Do you remember that? As x increases or tends to infinity, f of x increases, or in this case tends to infinity as well. So they're increasing functions there. Over here, if you have a is a fraction, isn't that what that says? Between 0 and 1, just think about that. It could be a third, a half, something like that. We're talking about raising a fraction to a power, and let's just check that out over here. A half and then square it would be a quarter. It's getting smaller, and then cube it would be an eighth, getting smaller. And that's what we see over here. There's 0.5 to the x, or a half to the x, and as x increases, or as x tends to infinity, the function is tending to 0 here. Okay, so this is a decreasing exponential function, or a whole family of them, decreasing functions. Do you remember that? Another interesting property, of course, is that when x is 0 in either one, over here as well, when x is 0, there, put 0 in as the power, a to the 0 is 1, with the proviso that a is not itself equal to 0, if you remember. So in this practical work, of course, we won't be trying to raise 0 to any power anyway. It's not going to make much sense in our work here, but we do have a common y-intercept. When x is 0, all on the y-axis, a to the 0 is 1. So here we are. Let's look at the properties here, summarised. And I'm taking screen clippings here from Hayes and Harris, their textbook for Year 12 Math Studies. So let's have a look at the properties. Here's the first one we've just talked about there. The graphs pass through the point 0, 1. Their graphs are asymptotic to the x-axis at one end. So in this case, tends to the y equals 0, the x-axis. And over here, for large negative x, this one comes down as well. Their graphs are above the x-axis for all values of x. Yep. Their graphs are convex. Yes, that's right. Remember, concave is turning like this. There you are in your little cave there. So they aren't like that at all. They're convex, so coming upwards. There's no cave. The cave is on the top, if you like. Their graphs are increasing for a is greater than 1 and decreasing for a between 0 and 1, or the fractions. Do you remember any of that stuff? Okay, well, we're going to keep working on it, so you'll play catch up there. Let's come down and have a look at what we want to do. Seen this before. This is Hutty's trichotomy for the derivative. Just remember, the derivative can be thought of as a straight process from first principles or rules, getting the rate of change or the slope of the tangent was the first thing we did. Remember instantaneous velocity with Newton, or the instantaneous rate of change. So I want you to think about that three aspects to the derivative. Okay, because what we're going to do is to study now, as I just said a while ago, that if we talk about this being an increasing function, then can you see the slope of the tangent's getting steeper? So it's increasing at an increasing rate. dy by dx is increasing as x increases. And dy by dx is, oh, here it is here, the instantaneous rate of change. So you can see an exponential function like this is characterised by a rate of change which is increasing. So it's increasing at an increasing rate. Not only is it going up here as x tends to infinity, but it's going up more quickly because the gradient is getting steeper. The gradient of the tangent is getting steeper. So we're playing with all of this. Around and around we go. I want you to be flexible in what you think of this derivative. It's basically a process, isn't it? But what does that mean? There are these two interpretations which you must be able to flick between depending upon what you're talking about in a function. Whether you are talking about graphs or how quickly it's changing. You might switch from talking about slopes of tangents to rates of change. So be flexible there. Let's have a look at some of these exponential functions. All right. Well, here's an experiment. This one doesn't come from Hayes and Harris. This is one that I've brought in, something that I used to work with bacteria. Weight of bacteria, WT in grams of E. coli present in a culture after T minutes. So a biologist or a bacteriologist, biochemist, was growing this at 37 degrees in nutrient broth. And he or she came up with this set of data. So there's the time in the top line. As time went by, he or she went into the hot room there and did these measurements every 20 minutes, it looks like, and recorded the actual number of grams of bacteria. I don't know. Are you into this? How would you do that? Well, you might have your little stirrer here. So you'll have your culture of bacteria maybe in a beaker here, and you'll have a magnetic plastic coated stirrer, magnet here, so I don't know whether you've seen this, so that'd be stirred. This is in a hot room. So every 20 minutes what would you do? Well, you'll have a digital balance here, take this off the stirrer, put it on here, record the weight, put it back. And let's see what the weight is. And you've previously weighed the beaker and the fluid in front of it, inside of it, and so the difference in the weight gives you a weight of bacterial culture. And so you're going to monitor this every 20 minutes. So this is an actual example now. And then, of course, you'll probably plot your data like this. Okay. Now, that looks like an exponential growth. It looks like it's going up and up and up, an exponential growth here. And that's what we usually do notice with this sort of experiment. Later on we're going to say, hey, can this go on forever? Oh, that's another question. That's an interesting one. If you're a biology student, you might already have looked at some of this. But anyway, let's go back and look at, what did we say? We were going to look at the derivative of the exponential function. Well, it looks like we got one here, an exponential function. The derivative is, rate of change. Let's have a little look up here at the rate of change of this. In the first 20 minutes, what is the rate of change? So this will be the average rate of change, won't it? Because we're taking it between points. We've not got the derivative yet. We don't know how to get the derivative of this function. We haven't even got the function. We've got the raw data, and it's indicating an exponential function. So let's have a look at this. This is a change of about 40 grams in that 20 minutes. Yeah, we'll have to round this off probably. Let's see if we just round that off. We've got a change, average rate of change of 40 grams per 20 minutes, or this is 2 grams per minute. Right, okay. Let's do it again. Let's go for the next 20 minutes. This roughly is 80 from 4. That's about a change here of, I think I've messed it up already, because 20 to 40 is only 20 here. Okay, that's actually 1 gram per minute. Now we have, so I just scribble this out, the change of 20. This is a change of 40 in 20 minutes, which is 2 grams a minute. Let's look at the next period, 80, about 80 to 160, just rounding it off. We're just looking at some average rates of change here to get an idea of what's happening with this little old exponential growth here. In, again, 20 minutes, it's 4 grams per minute. Hey, can you see what's happening? 160 to about 320. It's 160. Hey, this is about 8 grams per minute. And so on. Oh, that's interesting. Isn't that what we said that exponential growth does give? Its rate of change is increasing. In fact, we can say more. Its average rate of change is proportional to the amount present. Amount present. In other words, the more you have, the greater the rate of change. And that's what we sort of see from this graph here, don't we? It's changing at a greater rate. Oh, well, that's interesting. Would you expect that? Let's look at it practically in a context. The context, if you got bacteria growing, okay, so what's the cycle? They get bigger, then they start to divide. So the more you have, the more of this process is going on. So it's going to, you would expect to have a greater rate of change. You've got more bacteria doing that process and producing more. So it all sorts of adds up. But what we'd like to know is not an average rate, but at one instant in time, let's come down here, at one instant in time, how rapidly is that culture changing in weight? All right, well, what we need to do, therefore, is to find a function for this exponential growth and find if we can get the derivative of that, because that's going to give us the instantaneous rate of growth. Do you remember this stuff? This is Newton's problem in biology, mate. Instead of finding an instantaneous velocity, we're finding instantaneous rate of growth here. This is good stuff. Let's come down and do some maths now and see what we can come up with. Well, here we have it. Let's try to find the derivative. This is from Hayes and Harris now. We're saying we, from that empirical or experimental data, reckon we got one of these. We reckon we got a to the x. We haven't tried to fit mathematically a function to it. I don't know, you might have liked to do that. Do you want to do that? Let's go back and see if we can just have a look and what would the function be? I don't know, you've done this in previous years. Can we estimate from the data WT would be what? Well, there's our starting weight. Do you remember any of this? It'd be 20 times, now it's doubling, isn't it? So let's have a factor of 2. And to what power? How often does it double? What do we put up here in the power so we get doubling every, what is it? 20 minutes. It's doubling every 20 minutes. So we want 2 to the t on 20, don't we? So every 20 minutes we're going to, that's getting untidy there. Let's put here, so we'll have t on 20. So if you increase t by 20, so go for 20 minutes, that's 20 on 20 is 1, that's double, 2 to the 1. Then in 40 minutes, put 40 in there, 40 on 20 is 2. Yeah, this works. Hey, this works. We have got an exponential function. We've just done a little bit of maths on that to actually say with our technology what function would plot like this. Can you see it coming together? Isn't this exciting when you can actually do an experiment, then mathematically model it and explain what's going on there? Okay, let's go down and do the derivative now, because we can see it is possible coming out of an experiment to actually have a function. And if you've got a function, then maths to the rescue here. We're going to find the derivative of this little dude. Now, we're not going to worry about the number in front, the 20. we're going to say the important variation here, and that's what we're looking for, isn't it? Rate of change or variation. It depends on that second term, the a to the x, or 2 to the t on 20. That's what we want to look at, the rate of change of. We're looking at the derivative. The derivative is the slope of the tangent, or the rate of change of the function. So that's what we're looking at. Well, let's do it. Here's the first principles definition. This could be a bit hard. Been a while since you did this. So f dash x is a limit as h tends to naught of f of x plus fx plus h, take fx on h. And if we put our a in there, a to the x, it's a to the x plus h, take a to the x on h. And now we're going to look at a to the x plus h is actually a to the x by a to the h, isn't it? If you multiply two numbers together which are powers of the same base, you add the powers. So let's remember that rule. And so here we can actually factor out. So they've left a step out here. I'd like to put in another step, this one here, where we split up a to the x plus h, and then we can factor this out the front, and when you multiply that out you would get it. So we split it into two parts. There's a part here, limit as h tends to naught of a to the x. Well, there's no h's in that. So that's not going to vary as h tends to naught. Because they say here as a to the x is independent of h. So then we've only got this thing. So the derivative is, ooh, that's interesting. The derivative is itself, that's the function itself, isn't it? The function itself times by this. I wonder if it's possible to get a function whose rate of change is just itself. That's an interesting thing that's popped up here now. Is it possible that the rate of change of a to the x is itself? What would this have to be? This would have to be 1, wouldn't it? So if you wanted the rate of change of the function to be exactly equal to itself, we'd have to have this. I wonder if that's possible. That would be a really interesting little function, that dude. A to the x whose derivative was itself. Okay, let's go down and play with that. And so if we say h is very, very close to naught, then a to the h take 1 on h would have to come to approximately 1. We want this to disappear. This is one up here. We want this to be 1. Limit as h tends to naught. So we'd say if h is very close to 0, this would be 1. That's what the limit means. So therefore, a to the h would be approximately 1 plus h. Again, they've left a little bit out here. A to the h take 1 would be approximately, I'll use that squiggle, approximately h. And then a to the h is approximately 1 plus h. Okay, just going from there to there with a bit more detail. So now for technology purposes it's probably better, you'll see this in a minute, to let h be 1 on n and then call that large N. So that would have the same effect, making that power h approach 0 by calling it 1 on n and making n large. It's going to be easier for technology then. So we're writing this all in n land now, where h is 1 on n and is tending to naught, so n is tending to infinity. So here we have it down here. To make this limit be 1 as h tends to naught, a would have to be approximately 1 plus 1 on n to the n, and n would have to be getting very large. Now, let's not get confused here. Why have we gone to n land? This is easier to investigate with technology. Easier to use technology and put in bigger and bigger n's here. N tending to infinity implies h is tending to naught because h has been replaced by 1 on n. Okay, so what we want to do now is see, is this possible? Is it possible to find a special a such that when it's the base of your exponential function, its derivative or rate of change function is itself? Interesting stuff. Come down and let's see what happens. Yep, here we have it. If you actually put in larger and larger values, and we are talking about very large values here, what happens? Hey, what is happening to this function value? 1 plus 1 on n to the n. Because we said if n gets very, very big, that's equivalent to h tending to naught, a would be the result of that. It would approach the a value. Oh, hey, look at this down here. It's approaching some value. It's steadying up. It's only changing the very, very last decimal place. So what we're going to say is as n tends to infinity, this thing converges. Okay, we say it converges, this expression converges on an actual value. Now, as n tends to infinity. So that's the problem though. We can't actually terminate the decimal because we can't do n tending n at infinity or an infinitely large n. There is no such thing. Yet we can see that this is heading towards a certain value. And so we're going to say it converges and that there is an actual value for A. It's approximately this. And of course you've seen this before. An irrational number like pi. An irrational number. You know it's converging, you know there's a value for it, but it's got an infinite number of decimal places, if you like. So you can't write it as a terminating decimal or as a recurring decimal. No, it's irrational. And we're going to let E be the symbol for it. Now, mathematical notation is always pretty common sense. What have we done? Hey, what have we done? Our function was a to the x. Its derivative is itself. Only if and only if, which is this way, a double implication sign. But it is used, this word, if and only if, means this is the derivative, if and only if A is the special number that's doing this stuff up here. So we're going to say A is, what's the special number? Hey, let it call it be E. Let it be called E, sorry. Right? E, because it's a special exponential base. The special exponential, E for exponential base. We knew we were after an A to the x type, dude. We could see it from the function. We actually made up a function like that. See it from the graph of the function in our work. And now that we've found there is a possibility to get an exponential base such that the e to the x function has its own derivative. It is its own derivative. So this is a monumental finding, because obviously a very, very special function whose rate of change is equal to itself. All right, let's have a look at doing some maths with it and see what you think. So here we've drawn it now, and just summarising it, it's called exponentially, or the base of exponential function, the base of such groups of functions. And here's our result now. The derivative of e to the x is itself. So how would it plot? Oh, I think you recognise this back from the first screen. But if it's e to the x and it's 2.718, etc., well, it's somewhere between, what are we going to do here? Let's do this. So this would be something like 3 to the x and 2 to the x. Closer to 3 to the x, isn't it? Oh, well, I haven't drawn that closer to 3 to the x because it's 2.718, so here 3 to the x would come in there somewhere. So it's really going to graph very similarly. When you put x as naught in here, you're still going to get 1. E to the naught is 1. So it's an interesting one, because the graph makes it look just like any old exponential graph, but the secret is the rate of change of this, the rate of change of e to the x with respect to x, is itself. So, what's another interesting point? Remember the trichotomy? At any point at 1, what's the slope of the tangent? E to the 1. Oh, that's interesting. Right, the slope of the tangent is equal to the function value. And at 2, what's the slope of the tangent? E squared, e to the 2. Hey, this is a tricky dicky function. Interesting, isn't it? It's got the usual behaviours though. For large x coming out here, it's an increasing function because e is greater than 1. Greater than 1. E is approximately 2.718. So, and over here, come over to the left here, as x tends to negative infinity, e to the x does what they all do. Become asymptotic. All the increasing functions, that is, become asymptotic to the x-axis. Let's just check that. E to the x, okay. Let's put a negative in there. E to, let's say, a big number, e to negative 100. Why does it get small? It's 1 on e to the 100. Remember that. Okay, so that's going to tend to 0 if we keep changing this. A negative power means 1 over. So over here in this negative power land, it's going to tend to 0. Okay, one very, very important thing to notice in this course is that e to the x is going to be greater than 0 for all x, like all the increasing exponential functions here. All the exponential functions above the x-axis, aren't they? So therefore, the function has only a positive value for all values of x. E, a positive base, raised to the x cannot be a negative. Just remember, e is a positive base. Okay, so you're raising any positive number to even a negative power. Remember, a negative power doesn't make the number negative, it's 1 over. Alright, so how are you going there? A fair bit of maths here. Might have to rewind the presentation, just check out some of the stuff that was happening. Okay, let's go on now. Okay, so e obviously is a function. E to the x, sorry, is a function, but we might want to be doing other things with it. Like in the function we had before, had w t equals 20 by 2 to the t on 20. So we're going to build functions, aren't we, so that we can apply this to mathematical modelling. Well, what are some of the functions that might come out? Oh, it could be anything like this. Oh, we're going to have to go back and do things like the product rule. Can you see that this has got 2 parts here, x squared and e to the 2x? And for a start, though, we're going to have to use the chain rule. Because what if you had e raised to a function in x? We don't have e over here. Come over here. We don't have e, but we've got 2, and this is a function in t. It's not just to the t. So what do you do with that? Alright, well you could do what the book's got here, call f of x u, alright, and then so that you can see, you can see to do it in 2 parts. Do dy by du, that's the e part, and then multiply by du by dx. Do you remember that stuff? This is the chain rule. And so they've derived it here. You get the derivative of e, which is itself e to the f of x, and then multiply by a derivative of the power. Let's revise the chain rule in simple form, or the function of a function rule. I prefer for students to think of it that way because you can see when to use it. X squared plus 1 cubed. Let's call that y. dy by dx. What do? You do this power first, 3 by x squared plus 1 squared, and then multiply by the derivative of this. And you produce a chain of derivatives. Okay, so there's the first one, and there's the second one. And this working in u is trying to do that theoretically. So let's do it without the u's over here. Y equals e to the f of x. Alright, first of all, dy by dx. What's the first function you've got? E. Derivative of e is itself, so everything stays the same, including the power. It's like what we're doing up here when we do the power. We don't change what's in here. Now we have to multiply by the derivative of this part of the function, which is the power in this case, which is the derivative of f of x, which is f dashed x. So that's a little derivation. This is all that you're required to do, is to actually do it. You don't need to actually put it all in U land there. That's not necessary. Alright, so just to finish off with some notation thing. This is unusual, but it is still used. X means e to the x. It means the exponent function, the exponential function, sorry. The exponential function. And the exponential function is this important little dude here, because its derivative is itself. I think the best way to get our head around this is to do some examples. So let's have a look at doing an example. I'll do one just here. What about if y equals e to the x squared? Let's do that one. dy by dx would be derivative of e is itself. Now you don't touch the power yet, you're just looking at the two separate functions, e, and then this function up here. So now we have to multiply by the derivative of this function using the chain rule, and we get our chain of derivatives. It's a function of a function. So you look at the first function, which is e, then the second function. When you do the first function, its derivative is unchanged, because that's the special nature of e. And then multiplying by the derivative of the second function. Let's come on down now, and there we are there. It just flicks straight in there. So find the slope function for y equal to this. Okay, so let's have a look. Let's go through this one. So dy by dx, let's get the derivative of the first term. Well, you've got two lots of e to the x, so you've got two lots of its derivative. Derivative of e to the x is itself, so that didn't change. And then this term here, derivative of e is itself. Don't touch the power yet. The derivative of the power goes there. That's the second function. E was the first function. Its derivative is itself. Then the second function was there. You have to have its derivative. So therefore we've got 2e to the x, and to put this out the front, take 3e to the negative 3x. Alright, what about this one here? I mentioned this when we looked up before. That's a product of two terms in x. You've got to have two functions in x. You've got x squared and e to the neg x. So the derivative is, let's do, well, better put the product rule. What's the product rule? If y equals u, hang on, I'll put it up a bit high here, u on v, no, u times v, and u and v are functions in x, the derivative is derivative of the first by the second unchanged plus the first unchanged by the derivative of the second. Think of it like that. So let's do the derivative of x squared over here. It's 2x, second term unchanged, plus first term x squared unchanged by the derivative of e to the neg x. Derivative of e is itself. It's e to the neg x times by the derivative of the function in the power there, which is neg 1. So we've got then this little result here. Then the quotient rule. We've got two things divided. So let's write that out. Y equals u on v. The derivative, if u and v are both functions in x, first one, top line, the derivative of the top line, bottom line unchanged, minus the top line unchanged by the derivative of the bottom line all over the denominator or bottom line squared. Remember that? A lot more complicated. So let's do the derivative of the top line. That's itself times 2. Right, because you have this function up the top here. Bottom line unchanged. That's that one. Minus top line unchanged. Derivative of x is just 1. Are you remembering all this old stuff now? Alright, so tidying it up a bit, we can see we have a common factor of e to the 2x, so you could put that out the front, and then you've got 2x, take 1. So factorising. Do you remember factorising? I'll have to revise a bit of that. Okay, come down, let's do some problems. Okay, so here's the first little group, question 1 and 2. I would do most of these just to make sure, because this is going to be very, very important as we go into modelling of practical situations with this exponential function and others based on e. Alright, so pause the presentation and have a go. I'm going to go on and show you the solutions to these just down below, so you can toggle backwards and forwards and mark your work. Okay, so going on then. There's question 1. Okay, so just check that out. And question 2. Oh, we've just fit it in there. You notice that the book here is using u's. You don't have to put that u step in. Okay, so that's the rest of those. Okay, alright, let's move on to another example now. Alright, so find the slope function. Oh, same stuff. Remember Hutty's trichotomy. You've got the derivative, which is also meaning the slope of the tangent, and you've got the instantaneous rate of change. Doesn't fit in there. They all mean the same thing, different interpretations. Okay, so now we're looking at the slope function, which means we're still looking at the derivative. So therefore, we've got this function. You could call it u cubed. This makes a very long journey of it. I think you can go more like this. dy by dx equals, let's do the power part first, 3 times e to the x take 1 squared, then multiply by the derivative of this thing inside. Derivative of e to the x take 1 is just e to the x. Derivative of neg 1 is 0. So therefore we've got our answer there. You can tidy it up, mostly in tests and exams. When we're just asking for the straight derivative, it says do not simplify your answer. But if we're applying it to a problem, quite often you'll need to go on and write it in a simpler form. Okay, let's look at this one without the u's there. I think it's a bit time consuming to put it in u's. So here we want the derivative of this function. So there's 2 parts. There's a power function of this function. Let's do the power first. Neg a half 2e to the neg x plus 1 to the neg 3 over 2. Do you remember that x to the n rule? If y equals x to the n, the derivative is nx n minus 1. You subtract from this power 1, so you get neg 3 over 2. And then here we must multiply by the derivative of this. Derivative of 2e to the neg x. So the 2 is just how many lots of e to the neg x you've got. So you've got 2 lots of its derivative. Derivative of e to the neg x. Derivative of e is itself. But hang on, what's the derivative of the power? It's not just x in that power, so it's got a derivative, and its derivative is neg 1. So again, you've got the power function treated there, and then you've got the derivative of the bracketed function. Okay, and you could just leave it in that form, or you could put it in a simpler form. Let's put this on top now. Neg 2e to the neg x over here. What are we going to do? 2e to the neg x. Well, probably. Well, we could go into it, I suppose, and put here 2e to the neg x plus 1 to the 3 over 2, and we've got this half down there as well, so that's neg 2, so we could then cancel that, I suppose, and have that, and then we would have 1 over e to the x, 2e to the neg x plus 1, 3 over 2, putting this e to the neg x down in the bottom. Okay, so just clarify the power here. That's 3 over 2. So, yeah, so you can play around with them a bit. Usually, though, in tests, for this sort of work, just asking for the derivative and not applying it, we like you to leave it in unsimplified form so that we can actually see the parts of the derivative and be able to do the process correctly. All right. Okay, so let's go down and have a look at it some more, build up some skills now. So here's questions 3, 4 and 5. So have a look at those. Okay, and I'm going to just go down below there and show you the answers, and you can toggle forward and back, marking your work. So let's look at the answers now. There's question 3, or part of them. Okay, the rest of question 3 there. So down to question 4. Okay, so have a look and see what you think. Okay, let's move on. have a look at another example. Building up the skills here. Find the position nature of any turning points. Right, so this is slope of the tangent stuff again, isn't it? Remember, turning points from your earlier work are characterised by positions where dy by dx equals naught. Turning points. Local max or local min. So just recalling that. So again, you need the derivative of this thing here. So let's look at it. It's a product, isn't it? So the product rule is u dash v plus uv dashed, if the product is uv, both functions in x. Okay, so let's do the derivative of x take 2. It's just 1. Second function, e to the neg x, unchanged. Plus, first one unchanged. Now we have to do the derivative of this e to the neg x. Derivative of e is itself, but it's to the neg x, and the derivative of neg 1x is neg 1. Okay, so now we do have to simplify it, because we have to go and find the turning points. So let's take out the common factor. Here it is here, e to the neg x. And we'll put that out the front. And then it's 1 take x take 2. Do you remember factorising? Okay, so here it's 1. If we expand this here, neg by neg is a positive. So it's 1 plus 2 is 3 take x. And we can drop e to the x to the bottom line, because e to the neg x is 1 on e to the x. Alright, so we've got 3 take x on e to the x. So when is that 0? A quotient is 0 when the numerator is 0, 3 take x. You can't make the fraction 0 by playing with the denominator. So when you have this fraction and you want it to be 0, all you have to do is put the numerator equal to naught. A fraction can only be 0 when the numerator is 0. If the denominator is 0, it would be undefined. So let's draw a sign diagram now. So this is a little bit of the mini x-axis here. And 3 is our important value. So subbing in to the left into the derivative. So the derivative is this expression up here. So subbing in something like 1, we will get a positive. And then subbing in something like 4 here, 3 take 4 in the top line will be a negative. So we've validated the fact that it is a maximum there. So you have to actually prove that. To say that it's a maximum turning point, you must show the sign diagram here. So at x is 3, so we have to find the actual coordinates of the point. So when x is 3, we sub it back, not in the derivative, but in the original function here. So right back up the top, putting in x is 3 in there and getting that turning point. And we can leave it as e's in E-land. Probably preferable because e is an irrational number, so this is the exact form of the turning point, and we should state that. It's a maximum turning point and there its coordinates. Are you ready to try some for yourself? Let's go down and have a look. Question 6, I just skipped that. Hang on, I just come back a little. I'm trying to just give it without the answers here. I can't juggle that. Anyway, so here, find the position, nature of the turning points of those. I'd probably try to do most of these, I think. There's only 4 there from Hayes, and Harris. So have a go, looking for types of rules, product rules. It's a quotient rule, another product rule. Okay, so thinking through that and being careful with your algebra. Factorisation is going to be important here. Okay, so have a look at the answer then to question 6. And make sure you do the diagrams to indicate maximum or minimum. That's extremely important. Okay, we'll just come down and see that last bit there. Okay, so that you can mark your work. Alright, let's go on now. So can you see what we're doing? We're going through all the rules of differentiation and looking at what we can do now in exponential land. Okay, and what's the next one? I guess you knew it was coming. One of these mixed dudes. In other words, it's implicit. This is implicit differentiation. we've done this before where it's not y equals. We haven't got a nice easy one there. Y's are splattered in amongst the other terms. Let's revise this revision without the exponential function. Let's do something like x squared plus 2xy plus y squared equals 10. Remember this from before. Differentiating with respect to x, it's 2x plus, now this is a product, so let's bracket it up. The first term derivative of that is 2 by the second term unchanged, plus the first term unchanged by the derivative of the second, remember that, dy by dx. And then the next term, 2y, going to run out of room, dy by dx equals 0. So where we see these y's, it is implied within the function that they are functions in x. So we must, when differentiating, use dy by dx. Let's simplify it now. We've got 2x plus 2y plus in dy by dx land, we've got dy by dx out the front of 2x plus 2y equals 0. Okay, I've obviously chosen a nice one here. So dy by dx outside of 2x plus 2y equals neg 2x plus 2y. Therefore dy by dx equals neg 2x plus 2y over 2x plus 2y. So it's going to be neg 1. That's interesting. The slope of the tangent of this function is always neg 1. That's what it's saying. And do you agree with that? Okay. So you might think about that one. That was in one of the earlier tests, I think. All right. So the important thing is this line here. When you have y in such a function, you must remember it's implicit that y is dependent on x or is varying with x, and you must use a symbol where you see y for its variation with x. Okay, so come back over and let's look at this one, this implicit function, derivative of the first term, 3y. So it's just a constant, lots of, how does y change with x? Need a symbol. And then this is a product, so it's going to be the derivative of the first term, which is 2y dy by dx, doing the power, and then remembering that y itself has a dependence on x, so a symbol for that, and then second term unchanged, plus first term unchanged, derivative of e as itself, and then the right hand side. So you've got to keep your wits about you here. Some chain rule in there as well as the product rule. Okay, so it says find the slope of the tangent at a particular point. So now we're going to stick in x is 0 and y is neg 3. And if you do all of that, we can put in here 2y, there's y, e to the 0, just subbing in the numbers for x and y, and then rearranging it at the end. So you don't actually have to factorise dy by dx out here, right? You don't need that expression like I've done over here. You don't need that here because you're only evaluating at one point. So probably just leave it there and work with numbers and rearrange it with numbers. And so you've got the slope of the tangent. You could be asked, of course, to find the equation of that tangent. Okay, so what are we doing? We're going back over all the work we did before in ELAND, exponential, and in a minute logs as well. So here we are, find the slope of the tangent to that. Only a couple of these, so I think you need to do both of them to make sure of your skill level coming up there. Okay, so have a look. I'll take you down to the solutions now. I think that's, yep, those two there. So you can have a look at those. Generally, you will leave answers in ELAND because e is an irrational number and that's the most exact form for your answer, therefore. Okay, how are you going? Go back and check stuff, study the solutions carefully. Let's go on now. The natural log function. Oh, what's that? Okay, well, natural logs. Let's leave the idea of natural logs for a minute and just say, what about logarithms? Okay, so do you remember logarithms? I'd like to come down here first of all and say, well, if we had 2 to the x equals 30, we realise that is not as friendly as 2 to the x equals 32. Because 2 to the x equals 32 can be done easily without logs, because you write both sides as a power of 2. So that would imply this was your answer here. Now, because it's not 30, we have to still try to write both sides as power of the same base, but we're going to use base 10, and we're going to take the log of both sides, which is saying basically that we're looking at the power of 10 to get 2 and the power of 10 to get 30. That's that line there. And then dividing them, we've gotten our answer for x. We're using the log rules there. That is, back up here, going back, so you remember then, this is our primary use for it, and what we're going to do is say, if I have the log of a product, that's the power I need to raise 10 to get that product. It's the sum of the powers. Remember the product rule, that a to the m by a to the n is a to the m plus n. So because logs are powers of the base, you're going to use the power rules. You add them. For multiplication of two terms like AB, you'll add the powers. And then for division of terms, you subtract the powers. So if you're looking at the log, you are looking at the power of 10 here of a quotient. So you'll subtract the individual powers. Here it is here. Now just remember, logs are powers of a base. So here, the log of something raised to a power, well, what's that? A to the m all to the n. That's the one time you multiply powers together. So if you're doing the log of a to the n, you're talking about the power of 10 to get a to the n. So in log a, so it's n times the power. Right, so you're raising it to this power out here, you're multiplying the powers together. So that's the idea. And so if you've got powers of 10 and you're talking about logs, if you were to draw the graph, you'd be looking at 10 to the x goes through 0, 1, and the log, a long time ago since you did this, the log to the base 10 is the inverse function. It's reflection in the line y is equal to x, and it goes through the point 1, 0. This is y equals log to the base 10 of x. So what we're saying here, the question is going to arise, if you've got e to the x down here, then could you find log to the base e and make it easier to solve this problem? And so we go to base e logarithms called natural logarithms, because you think of the natural base e because of that derivative special property, and we actually use a different symbol for it. Log to the base e is ln, log of natural numbers, or Naperian logarithms, after the guy who did a lot of work with base e. We could call it that. We generally don't. We use log in that form for power of 10, and ln for power of e. Okay, so let's have a look at using those then. If we said e to the x equals 3, we would say, well, if we come over here and say, well, if I took the log to the base e of e to the x, that should equal log to the base e of 3. So I'm looking for the power of e to produce both sides. I'm saying those, if the numbers are equal, the power of e is equal. Now, do you remember the log of a number being the power of the base? So what would the log to the base e of this thing be? Well, it's self-evident, isn't it? It's got to be x, because the definition of the log to the base e of a number is the power you raise the base to. So you're finding the log of something which is already a power of the base. So it's just that power. So x equals ln 3. Okay, so that's the idea. Remembering the log of a number is equal to the power required to raise the base 2 to get the number. Okay. Okay, so that's our fundamental definition. Doesn't matter what the base is, it could be base 10 or now base e. So we're going to say if e to the x equals a, then x equals ln a, because x is the power of e required to get a. Okay, so that's important, and it's a double implication sign here, so it means if I give you this, you should be able to say that, and vice versa. Okay, so just revising this idea, don't get confused with logs. The logarithm, powers of a base, and now that we've discovered this special natural base e, we're going to use ln. Why? Because later on you're going to see a lot of functions, modelling functions with e in them, and we're going to see why that's important as well. Okay, let's go down and have a look at doing some work with ln, and I've already mentioned this now. So y equals ln of x means x equals e to the y, if you like, using that same idea. If y is the log of x, then y is the power, y is a log, y is the power of e to get x. And so you could write down a table of values for e to the x, a table of values for ln. That is on your calculator, of course. Next to the log button on the Casio, you've got log, and also next to it ln, and you could make up a table of values. And if you do that, you find that these two functions bear the same relationship as 10 to the x and log of x, which is base 10. We use that. So they are reflections of each other in a line y is equal to x. They're actually called inverse functions. One does the opposite to the other, if you like. We've interchanged x's and y's. When you reflect it in the line y is equal to x, you're interchanging x and y's in the function, as is mentioned up here. We don't do a lot of this theoretical work in this subject. It's more a utility math subject. I think that relationship between these graphs is important, and to get the idea that this is the point 0, 1, and therefore this is the point 1, 0. X and Y has been interchanged in the function. We don't do actually much algebra with those. All right, let's have a look at what you think you want to do now. Well, we'll probably have to just check that we are happy with working with logs in general. So first of all, do you agree with this rule here? E to the ln a is a. So what's it saying? I'm raising the base to what's this? ln a is the power of the base necessary to get a. Isn't that what ln means? The power of e necessary to get a. So you will obviously get a. That's another algebraic description of the basic formula. The log of a number is the power of the base. So if I raise the base up here to ln a, I must get a by definition. Okay. So here, another form, ln of e to the n is n. What power do I raise e to get e to the n? Well, the thing's written as a power of e. So the log is that power. Let's do another one. The log of e to the x squared. What power do I raise e to get this? Because that's what that's saying. ln is the power of e to get the number. Hey, the thing's already written as a power of e. It's x squared. I've scribbled over it. So the answer is x squared. It's a fundamental definition, if you like, of logarithms. Okay, so the laws are still the same, obviously, because we're just working with a different base. So we're still doing the same thing. Finding the power of e to get a product. It'll be the sum of the powers of e. Same reason here, because when I'm working with a product, then I'm summing the powers if we have the same base. And here, log to the base e of a quotient, two things divided, then it's the power of the top line minus the power of the bottom line. Just check it out. It's the same thing again. It's just now we're using in A land, instead of log to the base 10, we're using base e. All the powers will be treated in the same way. The power to get a to the n is n times the power to get a, because we're raising it to a power. It's a one time you multiply powers together. And just remembering here, ln a means the power of e to get a, and then you're raising it to another power. So you're going to multiply that power by the power of e. Okay, I'll have a little proof down here for that first law. If you look at the definition, a equals e to the ln a and b equals e to the ln b, do you agree? Right, I'm raising e to what's this called? The power required to get a, so that is correct. Same thing here, b is the base raised to the power I need to get b, and so I will get b there. So therefore, if you look at the product over here, AB is e to the ln of AB, and then we can separate it. Ln of a product is ln A by ln B, which is therefore the sum there, and therefore the ln of AB is ln A plus ln B. So that's actually a formal proof of what I was talking about up here, which was, if you like, an informal proof about why you would be adding up the powers or the logs, which are powers of the base e, to get a product. So this is a little bit more of a formal definition. That's not actually required in this course, but I think it's some interesting algebra if you're into a bit of mathematics there. Let's go down and look at some other results here and then do some problems. So if you think about things like what's the log of 1, so you can do it like this. Using the rules, I'd rather you think of it differently. The log of 1 is the power of e to get 1. Well, e to the naught is 1, isn't it? So therefore the log of 1 is naught, because naught is the power you raise e to. What's the log of 1 on a? What power do you raise e to get 1 on a? Well, we could say here that 1 on a is a to the neg 1. So the log of a to the neg 1 is minus 1 times the log of a. Right, using the power rules, and they've done it in a similar way up there. So there are some little tricky algebra pieces or special cases here, but you'll get used to those. So what's the log of e? They've done it a way here, you can have a look at that. But the log of e, by definition, what power do I raise? A log means the power I raise e to get e. Well, hang on, e is e to the 1. So that means the power I'm needing to raise e to get e is just 1. It's itself. So they are funny little businesses here, and you can get a little bit fooled by it, but I want you to go back each time and say any log, base e or base 10, log is the power required to raise the base to get the number. Now that's important. If you ever get stuck, then that's going to help you out, in addition to our algebraic response there. So the log is the power required to raise the base to get the number. And we're going to use base 10, but now base e, symbolised as log and ln. Okay, because of the importance of this little e. Okay, come down, let's have a look at doing something. Right, as a natural log equation. So this is actually practicing now use of logs, so breaking an expression down. So the log of the left hand side is equal to the log of this product, so breaking it, log of a product, the log of the first one plus log of the second one, and because this is a power of e, what is its log? Its log is just the power. Okay, just remember that here. Log of e to the n is n. So if you're finding the log, the power of e, and the doofy is already written as a power of e, the log is that power, isn't it? By that definition. Okay, let's do the second one here. Given a log, and log of n is all of this. Oh, hang on, what's our definition? The log of a number is the power of the base. So therefore n is e2, stick this up as a power. It says the log is this, so therefore it is the power, and then we can write it out, e to the 2.136 and e to the 0.358t. So it's just manipulations, because when we are modelling later on, we're going to be working with these with some reasonably complicated expressions, and this sort of behaviour or method uncomplicates it to a certain extent. Right, so can you practice that? Come down now and have a go. Question 1 and 2. Just taking a log of both sides and making sure you know the log rules. And just like the example up there. So you might have to toggle back and have a look at the example. I'll go down now, so you can pause this and have a go. Then come down and look at the solutions. Go backwards and forwards. So there are the solutions there for those question 1 and 2. Just building up your skills a bit with logarithms. Been a while. Okay. So moving on then. Let's have a look. Bring all this up together. I think questions 3, 4 and 5. Find without using a calculator these. Well, this is definition stuff. The log of a number. Okay, so over here, the log of this number is the power you raise the base 2 to get it. The base is e, and it's written as a power of e. Therefore, the log is just the power. Remember, the log of a number is the power you raise e2, or the base 2, to get the number. So let's have a look at this. E to the 3ln2. Oh, I've multiplied a log by another number, so that's a log of a power. Alright, so remember the rule there. If I have the log n times the log of a, it's the log of a to the n. And I can do it in ln or log land there. Okay, so we're going in reverse there. And now we're raising e to the log of 8. Hang on, what's the log mean? It means the power you raise the base to, which is e here, to get 8. So you must get 8. Right, remember the rule. E to the ln of a must give you a by definition, because ln of a is the power of e to get a, and you're doing it to e. So you must get a back again. Alright, so we have some problems down here. Just go through them and try to remember the idea of logs and the basic definition. Okay, so I think probably doing most of those is pretty important to get the skill level up. When you get through this, that's most of the hard stuff done then. We then want to use E and ln. Alright, come down and here are the answers to those. 3, 4 and 5. And you can toggle back and mark your work bit by bit. Alright, let's go on now. Some more work with logs, and I think we'll bring that up there just for the minute. Solving for x, and this is going to be important later on because we're going to be working with exponential functions. So e to the x equals 7. What will you do? Try to write both sides as a power of the same base. So obviously if you use ln, take the log to the base e of both sides, writing both sides as power of e, it brings this down, doesn't it? Log of e to the x is x by definition. A log of a number which is already written as a power of e is just the power. So x equals ln 7 from before. So the idea of finding the log of both sides goes back to your fundamental exponential equations. You're trying to write both sides as a power of the same base. Here you'll use e because this one's already written as a power of e. Okay, let's look at the second example here now. E to the x plus 2 equals 15 e to the neg x times e to the x. It was 15 times e to the neg x, sorry. Alright, now I would do this slightly differently. Where you see e to the neg x, I would always write it like that. I think it's easier for students to follow, and you can easily see then why they've done this step. Multiply both sides by e to the x, so that you cancel that, because e to the x can't be naught, so you get this line there. So that's probably the easiest interpretation of what's going on. So when you have e to the neg x, e to the neg x means 1 over e to the x, so you tend to do this line there. Let's go on then. So we're up to this point. E to the 2x, just multiplying that out, e to the x by e to the x, adding the powers, it's not x squared. Multiplication is addition of powers in exponent land, and then e to the x by 2 is 2e to the x. Alright, so now we have this thing, and this is an interesting one. You have to spot here that this e to the x, e to the 2x is really, come over here, is really e to the x squared. They've left this step out. This is what is really happening here. It's a square of e to the x. So if you're good enough, instead of your x squared plus 2x, take 15, can you see it as a quadratic in e to the x? And so you want factors of 15, neg 15, 5 and neg 3, and factorise it like that. Now, that's okay if you're not bad at maths. I'm going to give you an alternative. When you see e to the 2x, first of all, call it e to the x squared, but then perhaps let p be e to the x. So it's more obviously you've got a quadratic. You've got p squared plus 2p take 15 equals 0. So can you see it slightly easier in p land? P plus 5p take 3, or if you're not much good at factorisation, you could use the formula for the roots of a quadratic. I'll show you that in a minute. But then you have to return from p land, you let that be e to the x, so e to the x is neg 5, or e to the x equals 3, and we'll go on from there. So that's what they've done here. E to the x is neg 5. You can't have that, because you can't have e's a positive base, e's greater than 0, so it can never raise e to any power to get a negative. A negative power, remember, is 1 over, so there is no answer to e to the x being a negative. You can't have this. Okay, so therefore e to the x equals 3, or x equals ln 3. Alright, now there's some options there. The most important thing, come over here, is to see that e to the 2x is actually e to the x all squared. So it's a quadratic in e to the x. And you could use this p method, or looking at it directly as a quadratic in e to the x. And if you have trouble factorising, you will have to use this thing, which I think is on the formula sheet. So that thing there, for the roots of a quadratic equation of the form ax squared plus bx plus c equals 0. This time, of course, the quadratic is not in x, it's in e to the x, or p over here, if you choose to make that substitution. Alright, so some thinking to be done there. What method do you want to use? Okay, and there's two choices. Really, you can first of all spot it as a quadratic in e to the x and factorise it, or spot as a quadratic in e to the x and use the formula, or replace e to the x with p, so you're working with a quadratic in p, and then come back in either way again, either using factorisation or the quadratic formula. Alright, come down and, have a go at a few of these. I think it's very, very important to try the neg x ones. They're going to come up a bit later on, because that's going to give rise to, and this one over here, it's going to give rise to e to the 2x, which will be e to the x squared, a quadratic in e to the x. Need to have that skill there. Alright, shall we go on? Let's have a look at the solutions to these now. Oops, we'll just come back down here a little bit. There's all of 6. Just checking your answers there. And then 7. Okay, so there's 7. Just check the rules there. Toggle backwards and forwards and check it out. Important to build up the skills here. Okay, let's look at another example. We're moving on. We're going to find the point of intersection of graphs this time. So you can see what we're doing. Now that we've discovered E, then let's have a look at working with it in detail. So where the two graphs intersect, you put the two y's equal to each other. That's a simple idea, isn't it? Let's remember now, if you're asking for, I don't know, let's say two graphs to intersect, doesn't matter what the graphs are, what is true about both of these points? Well, they only have one x and one y each. So in other words, the y coming from the formula of that curve or line and the y coming from the formula for this one must be the same at those 2 points. Okay, so if you put the y's equal, you're looking for any common points where the y formula from one graph gives you the same answer as the y formula from the other. And so you're always going to be doing this line, equating the two y expressions. Now, of course, you can get all terms on one side, so that's an important strategy. All terms on one side equals 0, and then, as we remember here, they haven't shown it, e to the neg x is 1 on e to the x. So to clear that fraction, you'll multiply through by e to the x. So come over here with me, and I'd like to rewrite that, because I think I would like you to go through this step next. So the book has left this out. Then we're going to multiply both sides by e to the x. E to the x times e to the x, adding the powers. It's not multiplying the powers. It's not e to the x squared. E to the x times e to the x, add the powers, e to the 2x. And here, this is going to cancel. So plus 3 equals 0. So we actually have a quadratic here in e to the x, and you're going to make your choice as to whether you factorise it as a quadratic in e to the x and go on to these steps, or here it is again, if you get a bit confused with that, replace it by p and go into p land and factorising or the quadratic formula if you're not sure. Or you could try it on the calculator, but generally they want you to show some steps, so you need to show the steps here. You could use the calculator, so p take 3 is 0, or p take 1 is 0, so p equals 3, or p equals 1, then returning to e land, e to the x equals 3, or e to the x equals 1. Okay, so you come back up here then now and you join in here. X is ln1 or ln3. So what's the log of 1? What's the power you raise e to get 1? It's 0. So x is 0 or ln3. Now you want the points of intersection, so when x is 0, sub it back into one of them. Doesn't matter which one you sub it into. E to the x take 3 is a simpler expression, so sub it into that, and you get y is neg 2, and then x equals ln 3, sub it in up here, so you would have 3 take 3 when you sub in e to the ln 3, which is just 3. Okay, are you ready then to make your answer? So the answer is 0 neg 2, that's this value, and ln 3 and 0. And you can check it with technology in graph mode. We'd be using the Casio here. Alright, so graph mode, and then I think in the Casio you want to go Shift F5 to G-solve and intersect. And so you can do that on the Casio. Alright, how are you going? Building up, isn't it? A little bit of algebra. This course doesn't get any more algebraic than this. This would be the hardest expression you'd be working with generally. So I want you to have a go at all three of these, and you might start them, see what's going on there, see if you can make sense of it. I'm going to take you down to the solutions to question 8. Now they haven't shown the actual technology here, so you can check it with technology. Make sure you got the hang of that. Okay, moving on. Let's have a look. The next little bit we want to work with here. Okay, consider the function. Now we're going to delve into exponential functions in detail. Want to find the x-intercept, the y-intercept and so on of this function. So let's do it. The x-intercept is when y is 0, so putting the function equal to 0. So e to the neg x equals 2. You can do it this way, or you could say 1 on e to the x equals 2, so 1 equals 2 e to the x, or a half equals e to the x, so ln a half equals x, which of course is the same as this, neg ln 2, ln of 2 to the neg 1, so I don't know whether you want to. I like you to think of e to the neg x always as 1 on e to the x, and multiply across and do it this way, either way. But what is the x-intercept then? It'd be ln a half comma 0, or they've gone to decimal form there. Either way. Y-intercept, sub x is 0 back in the function, there's a function up there, so it's 2 take e to the 0. E to the 0 is 1, like it is for a to the 0 in general, so it's 1. So the x-intercept should be written as y-intercept, sorry, should be written as 0, 1, and we should have written this up here as ln a half and 0, if you like, a completed point with a pair of coordinates. Okay, so then we want to find, oh hang on, we've lost our problem now. We'll just come down here, we're playing around a little bit. Show algebraic that the function is increasing for all x, so let's just go down and do that. Show that it's increasing for all x. So here's the derivative. Let's do the derivative here now. Can you see the derivative of 2 is 0? This is the function up the top here. So the derivative of 2 is 0. The derivative of neg e to neg x is itself. Then you must multiply by the derivative of that top power there, so you get e to the neg x, which is 1 on e to the x. Is it increasing for all x? Increasing means dy by dx is greater than or equal to 0 for all x. Symbol means for all. So, and e to the x is always a positive, isn't it? So therefore 1 on e to the x will also be positive for all x. Okay, show algebraically that the function is concave. So concave requires a second derivative to be negative. So we actually have to get the derivative of this thing here. There's the derivative of the original function. Derivative of e to the neg x is itself times neg 1. So that means it is, just pause that there for the minute. Okay, so coming back to that, okay, so let's have a look in here. So we've got our second derivative. We'll just stop this for a minute. So with our second derivative here, we've got neg 1 on x, 1 on e to the x, and therefore it's going to be negative. So we're just coming in here and having a look there at negative, and therefore it's always concave. Then finally our discussion of the asymptotes here. As x tends to infinity, e to the x tends to infinity. Can you see that? Yep. So, and e to the neg x tends to naught. So therefore what's it going to tend to? It's going to tend to 2. Okay, our original function is going to tend to 2. Let's go up and have a look at our original function right up here. So our original function up there is going to tend to 2 if e to the neg x tends to naught. So have a look at some functions now and try and do the same sort of thing now. So we've got a few here. So you might pause the presentation now and have a go. Okay, so let's have a look now at some solutions to that. We've got question 9 there. And let's go to question 10. Setting it out in the same sorts of way every time. Question 11. These are fairly important questions then. Okay, let's go on now and have a look at derivatives of log functions. Obviously, what we want to do is to draw the graph of this function, ln, so typical ln. There's no asymptote here, by the way, it just keeps increasing. This is a value 1 naught. And what we want to do now is to actually find its rate of change, don't we? It is increasing at a decreasing rate. The tangent through here is getting less steep. So our e to the x function, let's just recap on that. Our e to the x function looked like this, increasing at an increasing rate. Now, our log function is going to have a different behaviour, isn't it? Because it's the inverse function of e to the x. Well, this is e to the x. This is ln x. Then it's going to be increasing at a decreasing rate. So let's have a look at seeing whether we can find the slope of the tangent or the instantaneous rate of change then. So let's have a look at this proof. If y equals ln x, what does it mean? Y is the log of x. Y is the power of e to get x. So we can write it like that. X equals e to the y is the same thing. They mean the same thing. Let's now differentiate this. Derivative of x is 1. Derivative of e to the y is itself, but you have to multiply by the derivative of that y, because it is an implicit function in x. So it's dy by dx, again they mentioned by the chain rule. Therefore you can say 1 equals, now e to the y going back to here was the same as x. So we've been a little bit tricky-dicky and say now 1 on x is dy by dx. And they put here the idea of remembering where that came from back in that first line. So we have been able to, not from first principles, but by using the chain rule, get the derivative of ln. And there it is there. derivative of ln of x, or log to the base e of x, the derivative is 1 on x. And that's an interesting result. That's a nice easy result as well. Let's do some differentiation of our ln function now and find its rate of change, the slopes of tangents to its graph. Let's come down and have a look at what we have to do. Okay, so here what we're saying again is if you have ln of some function in x, then don't forget you do the ln, differentiate that, and then you must do the derivative of that other function. So derivative of ln is always 1 on times the derivative of that. Let's do a little example over here. What about y being the ln of, let's say, 3x squared? Okay, so the derivative of ln is 1 on whatever it was. You don't play in here yet though. You just do that first function by the chain rule, and then you must multiply by the derivative of this function, which is 6x. So again, you get a chain of derivatives. You have a function of a function, and you must have a derivative for each of those pieces, if you like, producing a chain of derivatives. You could, and I said before, generally we don't with straight differentiation problems, but you could simplify this and get 2 on x. You could actually do that. Okay, are you ready? Here's the sort of general rule we're doing. Ln of f of x is 1 on. So f of x is going to be there times by the derivative. I think you should just think through applying the chain rule rather than learn off in monkey fashion patterns as such. Okay, come down. Let's have a look at an example. Find the slope function for this and this function. So the slope function, or instantaneous rate of change, that's the derivative. So the derivative is, now, what are we going to do? 1 on k to the x. Don't like the setting out here. That's the rule. Let's do it over here. ln of kx. The derivative is, derivative of ln is 1 on kx. Multiply by the derivative of this function is k. So you could then cancel to 1 on x. Rather than this formula. I don't think so. I think it would be better. Let's do the second one in the same way. Derivative here is 1 on 1 take 3 to the x, doing the derivative of ln, multiplied by neg 3. Okay, think of it as those two separate parts, and that's going to give you neg 3 over 1 take 3x, or we could multiply top and bottom by negative 1, get 3 over 3x take 1, multiplying top and bottom by negative 1 to get that simpler form there. Okay, what about the last one up here? X cubed ln x. That is a product. So remember the product rule, u dash v plus uv dashed. Okay, so let's do the derivative of the first term. That's x cubed is 3x squared. Leave the second one unchanged. Plus first one unchanged. Derivative of the second term, here it is 1 on x. And then you can simplify it. Okay, are you ready? What are we doing? Same stuff again, going right through our rules for differentiation using our new log function, ln of x. Okay, come down. Here we are, finding the slope function. Slope, or instantaneous rate of change, means the derivative. So that's all you're going to do again, looking for function of function and product rules. Are there any quotient rules here? Yeah, there's a quotient rule there. I think you need to do most of these to make sure your skill level is coming along. Okay, let's look at the answers. We'll just go up a bit here. Okay, so there's part of question 1. I might just pause that and check it. Quite a few parts there. Okay, let's move on then to another example here. Okay, differentiate with respect to x. That's just a straight derivative, as is the slope, as is the instantaneous rate of change. So let's have a look at it. The log of those things multiplied. Just use the log rules. Let's break it up first. That's handy. I would not try to do one on and all that sort of thing in that form. Try and break any log expression up. Okay, so we've got to there. Now the derivative is easier. It's 1 on x, take 1. Can I just show you what not to do? Don't do. Why do we break it? Well, what's this? If you don't, then you say, okay, the derivative is ln 1 on x e to the neg x. Then you have to multiply by the derivative of this, which is a product. First one by second one unchanged, plus first one by the derivative of the second one, which is that. What a monster! Okay, so don't do that. Try to break any log of a product or other expressions into separate logs and do them separately. It comes out much more easily. This will come to the same thing. There's just too much algebra in it. Okay, so this would be marked correct, but if you're in a practical problem wanting to go on and use it to find the slope of a tangent, it is very, very messy. It is correct, however. Alright, let's look at the second one. Log of a quotient. Break it up. It's the log of the top line minus, look out for the bracket here. Okay, bracket's important. Minus the log of the bottom line, because a quotient here is a subtraction of powers, or subtraction of logs. Remember, the log is the power of e. So then we can do 2 ln x and break this further. A log of x plus 2. Over here, minus log of x plus 2, and the log of x take 3, because here that's a product, so it's a sum of the logs, then removing it and making sure there's a negative through the whole bracket, and then we can differentiate. So all of this is simplifying y first, and then you do the final differentiation, because this would be a big mess to do 1 over that and then multiply by the quotient. Too hard. Okay. Come down and see how good you are in simplifying these after using log rules. Write an appropriate form, differentiate. Okay. Have a go. I'll take you down to the answers now. Yep. Okay, so there they are. Just check that you've used the rules correctly for logs. Okay, let's move on. Okay, so here we have some show that's. Again, what are we doing? Going through the same process as we did before. Can you differentiate anything with log in it? Okay, so show that the derivative of ln y is that. So let's do it. Derivative of ln y is a derivative of ln y times dy by dx. That's a chain rule. Alright, so do the derivative of ln y, that's 1 on y. Then you must multiply by the derivative of y with respect to x. So this is back to what? Implicit derivatives, or implicit differentiation, because this is an implicit function. Y is obviously dependent upon x, but we don't know how, so we must use the symbol for the variation of y with respect to x, dy by dx, where we see y. Let's have a look at the second one. Find dy by dx there. So you can recognise it is the same stuff, because y is hidden within the line. It is not y equals. Y equals is an explicit statement of y as a function in x, and that's easy to deal with generally. So let's differentiate both sides. That's what they're saying here. The derivative of a product. Derivative of the first term by the second term unchanged, plus first term unchanged, or derivative of ln y is 1 on y dy by dx. then derivative of y squared is 2y dy by dx. Derivative of x squared is 4x. Now what can we do? Same as before, we're going to collect up dy by dx's. So they've just simplified this a little there, and now bringing this across, we've got dy by dx and x on y, take 2y. That many, take that many dy by dx's, and moving ln y across the other side, 4x take ln y. So now we can do that division and leave it like that, or you could multiply top and bottom by y to get this form here, because we have that fraction in the bottom line. When you multiply that by y, you get x, and you must do the same to that and right through the top line as well. So you could have that form. Alright, are you ready? Can you see you're really building up a lot of skills here? It's good. Hang on in there and see how we go. Alright, so we'll just, hang on, just go back a little here and we'll go to there. Okay. So there we have a few little implicit ones, not too many here, so I think you need to do all of them just to make sure of getting the hang of it. Okay, have a go, come down and look at the answers in a minute here. Okay, so there are the three parts, just showing the little bits, and here for the product rule and so on. Okay. Alright, so mark your work. Hope you're going well. Hang on in there. Let's try and wrap this up now with a little bit just to finish off with. So let's have a look at this next one then. We've got find dy by dx for a creature like this. Now this is very messy. So a good trick, here it is here. Rather than try and differentiate this directly with the quotient rule, because it's so big and nasty, let's take the logs of both sides and see what happens. So we change it into a sort of implicit one here, a log of y. So differentiating now, log of y, log is 1 on, then dy by dx, and then you can see the quotient becomes a subtraction of terms. This is a good trick. Okay, so subtraction of terms, and the derivative of this, derivative of ln, is 1 on, 1 take x squared, then multiply by the derivative of this, which is neg 2x. Then take 4, derivative of ln is 1 on, and then multiply by the derivative there. So it does become quite a bit simpler to work with. Now let's have a look at what we've got here. So multiplying both sides by y. So first of all, this has been simplified to neg 1 on x, a half times neg 2, and neg 4 times 2. So those two terms have gone in the bracket. Multiply across by y, and you could then replace y by what it was originally. So it is a big nasty creature, and it gets very, very messy if you don't use logs. Let's look at x to the x and the derivative of x to the x. Well, your thinking here is quite simple. You can't actually differentiate any exponential function apart from e to the x. Okay, so therefore you must relate this somehow to e to the x. Let's look at what they've done here. Y equals x to the x. Take the ln. ln of y equals ln of x to the x. And then, of course, it's raised to a power, so ln y equals x ln x. Differentiating then, derivative of ln is 1 on y times dy by dx. Then the product rule here, derivative of the first one is 1, second one unchanged, plus first one unchanged, derivative of the second one. And so we can then multiply across, well here this is ln x, and that will cancel plus 1, multiplying across by y, so it then becomes dy by dx equals x to the x ln x plus y. So that's a fairly difficult one. But you can see there how logs are important in being able to break that expression down. Alright, let's have a look at some problems like that then. Okay. Here's a big mixed bundle here. And so you might have a look through. I think there's an interesting one here. Gives you a hint how to get the derivative of any exponential function. You have to relate it back to e to the x, because that's our fundamental exponential function, and we know its derivative is itself. So you must relate any power expression back to e to the x, and they give you a little hint here. That's an important question, question 5. Okay, have a look. I'll just show you the rest of them there, down to 9. And then we'll go down and have a look at the answers now. Okay, there's parts of question 4. Fair bit of work in those. Let's go back up there a bit. Oops. Let's come down. Okay, 4, 5 and part of 6 there. Seven and 8, and we'll just do 9. Okay, so there we have it, and hope you've done well there, and I look forward to seeing you in the next presentation. For now, it's cheers from me.